Welcome back. In our previous session, we explored the fascinating world of image acquisition, which allows us to capture stunning images of living organisms at a microscopic level. Now it's time to delve into the post-acquisition stage, where we learn about the role of image processing in turning raw data into meaningful information. When we capture an image of a biological sample, it's often too complex to understand at first glance. That's where the image processing comes in. It's a set of techniques and algorithms that allow us to analyze and extract meaningful information from images. There are several types of processing techniques that we use in biology, including filtering, segmentation, and feature extraction. First is image filtering, which is a crucial step in image processing as it removes noise and unwanted information from the acquired images. We use different types of filters to enhance certain features and limit the analysis to the region of interest to improve our target signal. There are various image analysis tools available to perform this task, ranging from manual selection using a mouse to sophisticated machine learning algorithms for automatic detection. Second is segmentation, which is a process of dividing an image into different parts, that is, process of identifying and separating object of interest within an image. There are several general methods of bioimage segmentation, from simple intensity-based thresholding to machine learning-based methods, and in the recent scenario, deep learning-based methods, which are a new approach using the convolutional neural networks to identify and segment objects. Finally, feature extraction is the process of identifying and measuring relevant features or characteristics within an image, which can then be used for further analysis or classification. These features can include shape, texture, intensity, and spatial distribution, among others. There are various techniques used for feature extraction, such as edge detection, texture analysis, and object recognition, among others. Now, let's take a closer look at some of the most commonly used image processing tools and techniques in biological research. One of the most popular tools is ImageJ, an open source software with a wide range of image analysis capabilities such as image processing, segmentation, and quantification. Fiji is a distribution of ImageJ aimed for advanced image processing tool with many plugins and functionalities. Fiji provides a user-friendly interface with a wide range of analysis tools including 3D visualization, tracking, and registration. Now, let's take a closer look at some of the most commonly used image processing tools and techniques in biological research. One of the most popular tools is ImageJ, an open source software with a wide range of image analysis capabilities such as image processing, segmentation, and quantification. Fiji is a distribution of ImageJ aimed for advanced image processing tool with many plugins and functionalities. Fiji provides a user-friendly interface with a wide range of analysis tools including 3D visualization, tracking, and registration. Another widely used tool is Cell Profiler, which is a free and open source software designed to analyze, measure cell images automatically. It provides numerous functionalities to measure complex cell structures such as counting and measuring cell shape and size. Recently, Napari, an open source multidimensional image viewer, is gaining a lot of popularity among the scientific community, which is again a powerful tool for visualizing and analyzing complex biological images with features such as interactive image viewing, annotation, and analysis. It has a highly flexible and extensible architecture which makes it easy to integrate with other image processing tools and frameworks. Additionally, being built on the Python programming language provides numerous advantages for performing post-processing tasks. Image processing using deep learning and artificial intelligence is a rapidly growing field in bioimage analysis. One of the most popular deep learning architectures used in image processing is the convolutional neural networks, CNN. CNNs consist of multiple layers of filters that extract increasingly complex features from the image data. These features are then used to make predictions about the image, such as classifying it into different categories or detecting specific objects within the image. It's also important to know that the AI-powered tools generally demand high computational power, which can be a pitfall if you have a lot of data and inadequate computational resources. Certainly, after learning about the various image processing tools and techniques used in biological research, it's essential to understand how to select the most appropriate tool or combination of tools for a given research question or dataset. Here are some tips that can help. Firstly, it's important to evaluate the complexity and size of the image dataset. Depending on the type of data, some tools may be more appropriate than others. For example, if the research question is focused on analyzing cell structures, tools that can perform cell segmentation and feature extraction may be more suitable. On the other hand, if the research question involves analyzing changes in protein expression levels, tools that can perform quantification and analysis of fluorescence intensity may be more appropriate. When it comes to image processing, each tool has its own unique features and capabilities. It's important to consider the ease of use and availability of support or documentation when selecting the right tool for your research. In order to find the best approach for your research question, it's necessary to evaluate the tools based on their ability and experiment with different tools or combinations. Don't hesitate to try out different tools and combinations to see what works best for your specific needs. Although both image acquisition and processing might be two different steps while approaching a research problem, both of them have a mutual feedback. If you have terrible images which is really hard to process, it just means it's bad and you have to go back and improve the acquisition. So it's always necessary to plan your image processing steps with pilot experiments and standardize the whole workflow before doing the actual experiments. I hope that this session has provided you with a general overview of the concepts and components of image processing and their practical application in the field of biology. If you want to explore image processing further, there are many resources available online. Specifically, you can check out websites like ImageSC forums and Noibias for detailed tutorials, forums and user communities. Remember, learning image processing is an ongoing process and it's always good to keep exploring and experimenting with different tools and techniques. Thank you.